For the last part on simple regression models, we would like to discuss the expected value and the variance of the OLS estimators. So one thing you may not notice that the estimated regression coefficients, namely the beta 1 hat and the beta 0 hat, they are actually random variables because they are calculated from a random sample. Right? So the data what we get is coming from a random sample, which means the numbers here are all random variables. Okay, so and beta 1 hat, for example, is a function of these random variables. Therefore, itself is also a random variable. Okay, and so does beta 0 hat. Okay, therefore, it's natural to ask what is the expectation and the variance of these random variables. Okay, beta 0 hat and beta 1 hat. What are the expectations? Okay, or expected values and the variance of these OLS estimators. So this may be a little bit difficult to understand by far, but it's kind of important. Okay, so for you to fully understand the rationale behind our practice. Okay, so in terms of actually doing empirical research, it is not that important. But some of the issues are important actually. You have to address when you uh, uh, choosing a appropriate method to do a regression. Okay? So to study the expected value and variance of these betas OLS estimators, we have to impose some additional assumptions for the linear regression models. First of all, okay, we assume that the true relationship in the population, the relationship between y and x is linear. Okay, it is exactly the regression model that we want to estimate. Okay, so this is by default. Typically, we don't challenge this assumption. Okay, the second assumption is that the data set is composed of a random sample drawn from the population. Okay, so which namely each observation is a random draw from the population. Okay? Moreover, each data point therefore follows the population equation. Okay? This one. So uh, we would have a lot of data, but actually it is very restrictive to claim that your sample is a random sample. In practice, it is very difficult to achieve. So use wage and education as an example. To have a random sample, we have to first of all we have to specify the population, which, for example, it can be all workers of country A, of US or China. Okay, and in the population, a linear relationship between wage or log of wages and the years of education holds. Okay, so typically we don't challenge this assumption. And how can we obtain a random sample? We do this procedure. First, we draw completely randomly a worker from the population. So you can use some, you know, by, for example, tossing a coin using some random number generator, okay, to pick randomly a worker from the population and record the wage and the years of the education of the worker. Okay, so it's a randomly draw. Okay, and then we throw back the worker into the population and repeat the random draw n times, so that we get a random sample of wage and education of size n, okay, namely with n observations. Okay, but in practice, if we really follow this procedure, will be very difficult. Okay, first you have to, for example, number every worker in a way, and then I think this is the most difficult part, which is number every workers. So typically, what we do is randomly, for example, draw some. Uh, Suppose you consider all workers in China. First of all, you can say randomly draw some cities, and within the city, you then randomly draw some factories or companies, firms, and then within each randomly drawn firms, you then randomly draw some workers. Okay? But regularly speaking, this is not a fully random sample. Okay? There will be a little bit statistical issue, but typically in the practice, we don't challenge this assumption as well, okay? Either. And the third assumption is that the sample variation in the explanatory variables. Okay? So what we require is that in the sample, the variance of x is greater than 0, or total variation of x is greater than 0. Okay? So this is also called the total variation of x. It is equivalent to require that not the values of the explanatory variables are not all the same. Okay. So because we want to study the relationship or study the effect of x on the explained variable y. Suppose in your sample x is not changing, then you don't know how well the change in x induce the change in y. Right? So you have to have there's some change or variation in x so that you can study the relationship between y and x. Okay? And the last assumption that we have mentioned, and it is the most important one, which states that the conditional expectation of ui conditional on xi equal to 0. Okay? So this assumption we have explained, it states that the value of the explanatory variable must contain no information about the mean of the unobserved factors. Okay? So basically, it requires that x and u are uncorrelated. You can understand it in this in this way if it's more intuitive. Okay, and this one is often the most important one when you apply OLS estimators. Okay, when you use OLS estimators to do estimate betas, and you have to be cautious on this assumption, and very often to address this one in your applications. Okay. Then we have a theorem that says that suppose we have the first these four assumptions SLR1 to SLR4, okay, the four assumptions that we have mentioned, then the OLS estimators are unbiased. Okay? That is, the expectation of beta 0 hat equal to beta 0, and the expectation of beta 1 hat equal to beta 1, the true population parameter. Okay, so this is a very useful conclusion. Right? It basically ensures that, or it justifies that why we use OLS estimators. Suppose SLR1 to SLR4 holds, then using OLS estimator, okay, then they are unbiased estimators for these betas. Okay? But notice that unbiasedness doesn't mean that the actual estimates that coming from the random sample is equivalent to beta 0. Okay? In the practice, the estimated coefficients may be smaller or larger depending on the sample. Okay, so because the sample is random, so we say that expansion rate beta 1 is also a random variable, right? So it can be greater than or smaller than its expected value. But on average, uh, beta 1 hat will kind of very close to beta 1, okay? In the sense that if, for example, we have several random samples of workers and their on their wages and education. Okay? We have several random samples, and in each of these random samples, we'll run the regression and get an estimated beta 1 hat. Okay? And for each sample, we will have a beta 1 hat. Right? And for this beta 1 hat, if we compute its expectation, compute its average, it will be very close to the true population parameter beta 1. Okay? But in just one given sample, the estimates one beta 1 hat corresponding to a specific sample may differ considerably from the true values. Okay, okay, that's about the expected value of the OLS estimators. Now we can discuss the variance of the OLS estimators. So here, we need an additional assumption SLR5, which is called homoscedasticity. Okay? Homo means the same, right? Scedasticity means the kind of the variance. Okay, so homoscedasticity means that the variance of ui conditional xi is constant to be sigma squared. Okay, and this particular value is independent of x. Is so no matter the value of xi is, the variance of the conditional variance of ui is constant, okay, or are the same. So this assumption is called homoscedasticity. Okay, So this assumption says that the value of the explanatory variable must contain no information about the variability of the unobserved factors. And SLR4, right, says that X contains no information about the mean of the unobserved factors. Okay, this this is a bit different. So this graph illustrates the idea of homoscedasticity. Okay? So we know that this is the population regression line. Okay? So it plots the average relationship between x and y. Right? On average, uh, if we know that x is equal to x1, then the expected value of y is on this point. But the actual sample, the actual data, is kind of changing around this number y, right? So and the requirement of SLR5, this assumption is basically says that for different points and different uh, expected value of y, it has different expected value of y, but the variability, the kind of dispersion of different the actual y's are largely the similar. Okay, the variability of the unobserved influence does not depend on the value of the explanatory variables. Okay, this illustrates the idea of homoscedasticity. Okay, if it is the other case, suppose for example, if x equal to 8, uh, the variance of y is very small, but if x equal to 16, the variance of y is very large, then this violates the homoscedasticity, and we call this heteroscedasticity. Okay, so hetero means different, right? Scedasticity means the variance, okay? Different variance across different x. So this is a violation of homoscedasticity. Okay. So given SLR1 to SLR5, we will have the following results. First of all, the variance of beta 1 hat equal to sigma squared divided by SSTX. I have said that this equal to the sum of xi minus x bar squared. Okay, this is the formula for the variance of beta 1 hat. Okay? And the variance of beta 0 hat equal to this one. Okay, I don't want to explain this. It's you know there's a formula, that's enough. Okay? But there are some common pattern here. Okay, so suppose the sampling variability of the estimated regression coefficients will be the higher, the larger the variability of the unobserved factors. Right? If sigma squared is larger, this variation of beta hat and beta 1 hat and variance of beta 0 hat will be larger. And the lower, the higher the variation in the explanatory variables. So if the variation, total variation of the explanatory variables SSTX is larger, then the variance of beta 1 hat and the variance of beta 0 hat will be lower, right? Will be smaller. Okay, that's a general pattern here that you need to know. Okay, so it says that basically sigma squared is higher due to the variance of beta 1 hat, for example, is higher. Right? But if the SSTX is higher, it leads to that the variance of beta 1 hat is smaller. Okay? and it's the same for beta 0 hat. Okay, so the formula tell us the variance of beta 1 hat and beta 0 hat, but practically it's a bit difficult actually to compute the variance using this formula, okay? Because in practice the sigma square the sigma squared is often unknown, okay? So what we do is we want to also first estimate this sigma squared so that we can estimate the variance of beta 1 hat and beta 0 hat, okay? So how to estimate this sigma squared? So recall that the sigma squared is the variance of ui conditional xi. But because we SLR5, the fifth assumption, states that xi contains no information about the variability of ui, so it equals to the variance of ui itself. And we know ui by construction, okay? If we have a linear regression, we can construct the estimate of ui hat. Sorry, we can construct the estimate of ui, which is ui hat. Okay? So we use ui hat to estimate ui so that we use the sample variance of ui hat to estimate ui, that is sigma hat squared. Okay? We use this sigma hat squared to estimate sigma squared. Okay? And because of the property of ui hat, it will equal actually ui hat squared, sum of ui hat squared divided by n. Okay? Okay, one could use this one to estimate those variance. Okay, but the problem of is that, so this is actually, if you still remember, this is SSR, sum of residual sum of squared. Right? This is SSR. So we can use this to estimate the variance of sigma hat. Okay, but the problem of this estimate is that it is not an unbiased estimate, or in other words, it is biased. So the expectation of this is not equal to sigma squared. So in the practice, we construct an unbiased estimator, which is 1 over n minus 2 times sum of residual squared. Okay. So this is the one that we actually finally use to estimate sigma squared. But why we need a n minus 2? It's a technical thing. Actually, there's an explanation in the Coursera MOOC video. If you are interested in, you can watch it. But still, I think it's a bit difficult to understand for beginners in statistics. Okay, but anyway, so here's the result, the theorem. If we have SLR1 to SLR5, okay, the 5 assumptions that we have mentioned, then the expected value of sigma squared equal to sigma squared. Okay? So the sigma squared, this one, okay, is an unbiased estimator for sigma squared. Okay, so uh, what we do to estimate the standard, the variance or the standard deviation of beta 1 hat is simply replace sigma squared with sigma hat squared. Okay? By replacing this one, we get and take the square root of this quantity, we get the estimate of the standard deviation of beta 1 hat. And we call it the standard error of beta 1 hat. Okay? So here it's so this is the again the estimated standard deviation, okay, of the coefficient. This is the estimated standard deviations of the regression coefficients, and we call them standard error. Okay, standard errors, and why we need to know this? Because they measure how precisely the regression coefficients are estimated. So suppose this is small, then we are pretty confident that the true parameter is close to what we have estimated. But if this is large, then the true parameter may be not very close to what we have estimated. Okay, so it measures how precisely the regression coefficients are estimated. Okay, so this is about the statistical property of the OLS estimators. So the bottom line here for you to remember is first of all the assumptions. Okay, SLR1 to SLR5, right? And SLR1 to SLR3 is kind of basic, and typically we take them for granted. The most important one is first of all the SLR4, which states that the expectation of UI conditional on xi equal to 0. No information is contained in xi about the mean of UI. Okay, and the other one is that the SLR5, the variance of UI is irrelevant, so, to the x. Okay, so this is also called the homoscedasticity assumption. This is called zero conditional mean assumption. So these are the important things that you need to remember, and also the results. Okay, the results, you don't need to know the how we arrive these results, but remember the results. First of all, SLR1 to SLR4 implies that the expectation of beta 1 hat equal to beta 1. Okay? Second, SLR1 to SLR5 implies that the expectation of sigma hat square, sigma hat square equal to sigma squared. Okay? And you need to know the formula of sigma hat squared, which is 1 over n minus 2 sum of ui hat squared. Okay? And finally, you need to know the standard error of beta 1 hat, which equal to square root of sigma hat squared divided by SSTX. Okay, these are the bottom lines that you need to know. Okay, just try to remember this, okay, by all your means to remember this. These are important. Although in the practice, it's not really relevant actually. So we will see these quantities. So I have seen about the primary introduction on softwares and how we implement simple linear regression in the softwares. Okay, later I will explain how we can find this, for example, the standard error of betas in the regression tables. Okay, not in the Excel, but it's also possible. It's also doable. Okay, and later in the when we move from simple linear regression to multiple linear regression, all the things are basically similar, except that we extend uh, one explanatory variable to many explanatory variables, and all the things are similar. If you understand everything about simple linear regression, then it's will be easier for you, okay, to understand the multiple linear regressions. Okay, so that's it for the part of simple linear regression.